Well, thank you, everybody. Can you all hear me? I'll take that as a yes. So most times when I talk to people about climate change, they envision something like these pictures up here of a glacier in Alaska receding or polar bears out on melting ice flows. I'm not going to talk about that sort of scenario this morning. I'm going to talk more about a very applied version of climate change vulnerability assessments that the fisheries program's been doing to look at how our hatcheries may or may not be able to function in the future given a changing world. So really the objectives of this, the first one is to really acknowledge that our hatcheries are a portion of the landscape and a portion of the ecosystem, even though they're heavily managed and controlled by us, and we can't escape whatever future climate is going to happen. We wanted to establish a quantifiable and repeatable method so that we could use the same method for multiple facilities and expand upon it for other types of facilities if need be. And it would be something that was rooted in numbers and something that was easy to follow, though that could be debatable. We wanted to present all of our results in a common currency that's used by hatchery managers and fisheries managers so that these assessments would be useful to the people who work there day to day and they could understand what we are talking about rather than just shout numbers that were meaningless or abstract. And finally, we want to deliver all these results to our stakeholders so that we can spur some proactive management and hopefully be able to deal with some of these issues now when it's feasible and hopefully cheaper than in the future when it could be expensive or already too late. So I'm sure many of you are familiar with this. This is the classic diagram of Pacific salmon life history. And these fish can be impacted by climate change in a number of spots. These first ones that I'm going to talk about are beyond our control. So adults, when they migrate to spawn, can hit thermal blocks in rivers. It's been proven that Bonneville Reservoir can get quite warm in the summer already. And when it gets about to, I think it's 21 degrees centigrade, adult fish stop migrating. And that obviously is a problem for a hatchery. No adult fish means no baby fish. Ocean acidification and changes to upwelling can impact the food chain in the ocean and potentially starve juvenile fish and change the numbers of fish returning. And you can also have thermal blocks and new predators that have invaded the area that impact the juvenile migrants when they're moving out of the system. But really what we need to contend with and what we can control is the hatchery environment, which you can think of as pretty much the freshwater rearing phase, because we take the adults in, we do the spawning, and raise the fish. And so try to think of the hatchery as almost that whole freshwater phase, but more or less under our control. So we developed this conceptual model, and like the modeling talk yesterday that had the lots of bubbles and lines, I've tried to simplify it down. There's a lot of numbers, there's a lot of relationships in this. If you want further information, feel free to ask. But we start with climate. In climate, we have a current set of climate variables, which is basically the last 10 years for each facility, and then a future. We chose the A1B model from the climate assessments and used the ensemble there. If you want more specifics and want to get into it, I will be glad to talk numbers. These climate models often put out two variables that are of interest to us: air temperature and precipitation, which we then use through downscaling techniques to predict the water temperature at the facility and the water availability at the facility, because those are two things that all hatcheries use, obviously. From the ambient water temperature, we derive the hatchery thermal environment, so what do the little fish inhabit, and whether or not that will cause problems or kill them outright. And then we build a fish growth model because as cold-blooded animals, warmer water means fish grow faster and more. From water availability and combining it with fish growth, we can look at indices for carrying capacity within the hatchery. And there's two indexes that are used all the time, which are density index, which is roughly is the amount of space sufficient for fish of a certain size, and flow index, which is the amount of water coming into the facility sufficient for the fish of a certain size. And these are two variables that are used commonly by hatchery managers, and they have thresholds for do not exceed. And it's been rule of thumb, and really each hatchery is different, and it's through trial and error that they know that if they exceed certain thresholds, either fish get sick and die or other bad things happen. So I'm going to go through 2 case studies today, and rather than present all the data, which I did in a dry run and my colleagues told me was way too long, really boring, and overly complex, I'm just going to talk about some of the novel stories between 2 of our facilities that we've completed so far. So the first is Winthrop National Fish Hatchery, which is in the red circle up there. It's in the eastern side of the state of Washington and pretty high up, pretty mountainous area. Here's a photo of the facility if you're not familiar with it. So Winthrop, being a facility that's in a higher elevation watershed, is very much impacted by snowpack for its needs for the year. So this blue line is the current historical baseline for the amount of snow in the watershed. The red line is what we're predicting for the future, and the yellow is actually the confidence interval around the red line. So what we see is a pretty drastic change in snow water equivalent, which is basically how much water is retained in snowpack that then melts and comes out throughout the summer. We see it go from about 12, 13 inches of snow throughout the watershed down to 10. So 3 inches of snow, while it seems like not a lot, is actually quite a bit of water. And we see that it has a pretty big impact on flows. So again here, the black line is the 10-year baseline, the red line is the 2040s prediction, and the yellow line is the mean around it. And what happens here, because this snowpack isn't there, essentially, or is falling as rain, we see a shift in the Methow River flow, so that freshet is about a month earlier than it typically is now, which again, to a layman doesn't sound all that different, but what that really means is that that water that's coming out is now not available in summer because it melted too early. What this means through the entire watershed, this is a depiction of drought possibility. So basically, what is the change in having the 7 driest years on record? Red is bad. Red is that there'll be 20% more chance of drought. Green is good, meaning that there'll be 20% less chance of drought. And we see that the vast majority of the basin is in these reds and orange tones, meaning that there's between a 5 and 20% chance that there's going to be more incidences of drought per year. And again, it's because the snowpack's melting, it's going away, and summer doesn't get the flow that it needs. A good side of this is that rearing temperatures within the facility remain fairly constant, even under the future scenario. So again, black line is the baseline, red line is the prediction in the 2040s. And we see that even though there's a little bit of increase in the high summer months, for the most time, either the future temperatures are predicted to be about the same or slightly less than what they were currently. This is a growth curve for the animals based on the temperatures. This is every month we look at relative what it would look like in the future versus now. So those aren't scaling to each other and they're not additional. And what we see so far is that earlier in the year, it's actually colder at Winthrop in the future than it is now. And so we have slower growth, and these fish will be a little smaller for a few months. But then as the warming takes over, the fish start to grow quite larger. And where it ends up is these animals end to be about 7% longer and 2% heavier. So larger fish, but not inconceivably larger. Where we really see an issue in how it'll impact the facility is flow index. So again, this is the amount of water available for the given size of fish. We also have this as a change in index. So every one of those 4 bars in the middle that's going up, that's an increase in flow index. And we see that the summer months, remember, with that lack of snowpack and lack of flow, we have a massive increase in flow index, especially in July, where it's about double what it is now. And the reason for this is because there's less water available to the facility, not because the water is higher temperature or that the fish are bigger. So really the tail of the tape for Winthrop is that loss of snowpack impacts water availability, and that produces the impact on the facility. Our second case study is Quilcene National Fish Hatchery. It's a very different system. It's over off of Puget Sound, rain-driven system. And here from the picture you can tell very lush, very green, lower altitude watershed. We again look at snowpack, same idea here. Blue lines are the historical, red line is the mean future, and the yellow line is the range. And another big decrease in the amount of snowpack. And when you first look at this graph and see the snowpack declining that much, your first thought is, okay, this is going to be a very similar story to Winthrop. They're going to have issues with summer flows. But this is a little different view of the flow regime for the basin. When we look at the mean flow throughout the year, we actually see increases in the amount of water in the basin. And the reason for this is because, with the exception of some of this area, which is very high elevation, the vast majority of the watershed that supplies the facility is low enough that there isn't much of an impact of snowpack already. And whatever warming doesn't change the rainfall. There's actually predicted to be more rainfall for the area throughout winter. We see that again in the severity of summer drought. The scale's a little different, but these higher elevation areas are what's impacted by drought, but it's only an increase of percentage of about 2 to 4%, so not very much. And then the vast majority of the basin is a percent increase between about 0.5% and 2%. So there's really not a huge impact of loss of water through the summer. But like I was saying, with the more rain in the winter, there are increases in the amount of flooding that could happen, especially at these lower elevations, where with more precipitation, it can actually have larger flows in winter, which could be damaging to the facility that time of year. When we look at rearing temperatures, though, we see something that's a little bit more insidious. If you look along this graph, every single month has a warmer temperature, and these temperatures in summer are up to a couple of degrees centigrade warmer than what it is now. And none of these violate anything that would kill the fish outright, but where the big issue comes in is the growth curve for these animals. Unlike Winthrop, where it's that cooling, that slowed growth at the beginning and then very moderate warming, here it's just straight warming and it's year-round and it's pretty high. And what we end up with is a fish that's 35% longer than they are now and 10% heavier, which is a pretty big change in the size of the animals at release. Again, unlike Winthrop, without changes in flow, there really was no issue with flow index, but with those fish getting so big, they actually outgrow their rearing containers. And we see at the last about 3 months of the rearing cycle, they strip out their density index requirement. So this red line is what they never want to exceed at the facility. They get close to touching it now, right at the very end, right as the fish are released, except that'll happen now 3 months earlier, which has some big problems for removing waste from the containers and keeping all these fish alive and healthy. So again, very different story here. It's the higher water temperatures that's driving the issues, not necessarily less water. So we've made some preliminary conclusions from these 2 test cases. Really, the impacts within each facility are dictated by the local environment, and it's not something that you can just look at from outside and say, yep, water's going to be warmer, they're going to be in trouble, or there's going to be less water. You really have to go through a lot of different scenarios and tailor each model to the facility. Winthrop, like I said, the impacts are largely related to decreased snowpack, which is altering water availability rather than wholesale increases in temperature. Whereas Quilcene is the exact opposite. The impacts are largely related to increases in the water temperature that are increasing fish growth rates and allowing the fish to get too large. In both cases, though, the good thing is that temperatures were not predicted to exceed their thermal tolerances for these animals at either facility. So it doesn't look like anything's going to be baking in raceways. It doesn't look like anything's going to die outright or be unable to reproduce. And one of the bullets I added towards the end is we've started to move on to other facilities, and this has really been a learning curve and data collection challenges. These facilities have been around for a long time, and through the years they have collected lots of data in different formats, and oftentimes it's hard to find. The other issue is that we got lucky with Winthrop and Quilcene that there was a USGS gauging station on both main rivers that collected temperatures. Now we've moved on to Macon National Fish Hatchery, and the gauging station there does not collect temperature, and it's become a much more difficult situation to make baselines for the current times when you don't have a lot of data. So we've moved on to some proactive adaptation planning. So here again is the model that we used. And really we wanted to sit down with our stakeholders and think about how can each of these facilities be impacted in the future and what can we do now. So in places like Quilcene, where the impacts are temperature related, there is the possibility of mechanically cooling water using chillers. It's very expensive. A lot of our facilities don't have the equipment, but it is a possibility. If the fish are growing too much, there is a capability to alter their rations and restrict their growth. When we presented the Winthrop data to the manager there and asked him, could you deal with a 7% longer fish? He said that would be easy. I could slow them down either at the beginning of their lifespan and take care of that, or we could feed them a little less throughout and take care of it, and it would not compromise fish quality at all. When it comes to carrying capacities within the facility, you can manage your water. You can either make sure that all the raceways are sealed properly. You can use reuse. There's been a lot of talk of different reuse systems and more intensively using the water we have. And if all else fails, though this is probably the most litigious change, you could change your production targets. If you try to raise 200,000 fish now and know you only have enough water to raise 100,000, that may be the change that has to occur. With that, I'd like to acknowledge all of our collaborators. We had our downscaled temperature models were produced by the Washington Climate Impacts Group. Chris Pasley and the staff at Winthrop National Fish Hatchery were invaluable for getting us data there, and Dan Magnuson and Ron Wong did the same for Quilcene. Bill Gale and Patty Crandall are the chairs of the Fish and Wildlife Service Climate Change Planning Team that we work under for producing the modeling data, and we received some support and funding from the Fish and Wildlife Service Region 1 Climate Board. If you would like any more information, I didn't get into the nitty-gritty, feel free to send me an email. We've also published all the details of our modeling in the Journal of Environmental Management. And if you want to see any finished products, they're on the fisheries page at the link that's up there.
It seems both for the Metal and the Quilcene that when we look at going from snow-driven to rain-driven, that the freshet's going to be quite a bit earlier. So the one thing I didn't see in the assessment in terms of futures is really looking at, okay, we're looking at accelerated growth, and it's really more along the lines of kind of phase 2 of this analysis is I didn't see anything for evaluating smolt to adult return rates on different strategies. So, one of those may be, okay, let's look at the accelerated growth and maybe look at some experiments to release fish early and evaluate with these future changes in hydrograph. That might be an advantage. So did you contemplate any of that or thought about that?
In the modeling section itself, we didn't look at that explicitly. We've discussed different strategies for release, for how would you change a program in the future when we've had talks with our stakeholders. One of the interesting things is like Quilcene moves fish off station into net pens in Quilcene Bay every year. And one of the things that's predicted to happen in the future is there's harmful algal blooms, and there are supposed to be more of them. And so one of the questions was, what do we do with these fish that are typically moved off station? Can we still do that? If we can't do that, what do we do instead? Is there another place to move them? And that got into the discussion of, should we raise fish and release them earlier? If they're too large, should we be releasing at different age classes, fry releases or something like that? We haven't explicitly modeled any of that, but it's in the discussions of how do you continue to operate under future scenarios. But that's a very good idea, and it's something that will have to be confronted and something that needs to be studied and understood.
All right, thanks, Kyle. So I was wondering if you could speak to like the timing of getting additional hatcheries reviewed. As I talked about yesterday, there's 15 national fish hatcheries and another 9 in the lower snake comp program. And you talked about 2 programs plus a couple more you're working on. I'm wondering, what's the timing for moving on, doing additional assessments, and any comment on any administrative or hurdles you're coming against for moving forward with this?
Yeah, so currently we're working on Macaw National Fish Hatchery and Quinault, which are the other 2 facilities on the peninsula, and we're trying to do them concurrently. After that, I don't know exactly how many per year we're looking at doing and which ones. It gets decided by someone who's not me. The biggest hurdle we've had thus far really has been data. We've had fantastic people to work with at each facility. We've had fantastic hatchery evaluation teams that have helped out, and our stakeholders so far have always come through and been very interested. The problem is just finding the data that we need in a usable format, or finding whichever data exists and getting it into a usable format. The other issue is that despite our greatest plans, there's something unique about each facility that we have to account for, and it's not just dumping numbers in and walking away. So it gets subtly more complicated every single time we do one of these. I think I'm out of time.
You are out of time, but thank you very much, Kyle.